sometimes frequency rates alone are not enough. As an example, look at this information that we have regarding race deaths by police shootings. This comes from the Washington Post data for 2015. Looking at this raw data, what impression do these numbers convey? Well, they tend to give the impression that more Euro-Americans are shot and killed by police. Thus, viewing this, one could come to the conclusion that a Euro-American individual was almost twice as likely to be shot and killed by police in 2015 than an African-American individual. However, a key piece of information is missing here. What we don't have included in this is the race population size. So, the percentage of the population that is Euro-American is not the same as the population size that's African-American Hispanic. So, here we have our Washington Post data for 2015 and the census data on race for 2015. So we can see when we look at this that Euro-Americans make up 77.1% of the population in 2015 and only 13.3% of the population is made up by African-Americans in 2015. Taking this and applying it to the total of the population number, we can see roughly how many individuals were Euro-American and how many individuals were African-American in 2015. So, since we have two different size populations or samples here, how can we make accurate comparisons? For that, we're going to use a relative frequency distribution. A relative frequency distribution uses is basically the same thing as a frequency distribution, except the class frequency is replaced by a percentage. This allows us to then make comparisons across groups. So let's take a look at this example. If we're looking at getting the percentage of the race population that's killed by police, we would need to take the number of individuals that are killed by the police and divide it by the population amount, and then times that by 100. So, doing that for your American population, we get 0.0002%. This is the amount of the Euro-American population that was killed by police in 2015. When we apply this to the other populations, we can see that 0.0006% of the African-American population was shot and killed by police, and 0.0003% of the Hispanic population was shot and killed by police. Now, taking this information, we can go back over and create a relative frequency distribution, and let's take a look at that. So, here we see a relative frequency distribution that combines both our deaths and the percentage of the race population. So, when we look at this information, what can we conclude? Well, we can see that more Europeans were indeed shot and killed by police than any other race in 2015, but the proportion of African Americans shot and killed by police was 3 times that of Euro-Americans. What this means is an African American individual was 3 times more likely to be shot and killed by police in 2015 than a Euro-American individual. Furthermore, an African American individual was 2 times more likely to be shot and killed by police in 2015 than a Hispanic individual. So notice, looking at the percentage of the race population gives us a very different understanding of the rates of death by police shootings, which is important for being able to move forward with appropriate interventions. Now, let's take a look and produce one of these ourselves. So, you're going to go through and construct a relative frequency distribution, combining the frequency distribution data in problems 5 and 6. So this is working through practice problem 15 on page 52. If you look at those distributions, you're going to see one is looking at the age of the actress when she won her Oscar, and the other is looking at the age of the actor when he won his Oscar. So, let's take a look at how we can go through and construct a relative frequency distribution for this data, and then what conclusions that can help us draw. So, first, you see here, we're going to list off our age of the actresses in years that won an Oscar with our different class categories, 20 through 29, 30 through 39, etc. I've copied down the frequency data from the table. Now, in order to turn this into a relative frequency, I'm going to sum those up so I get a sum of 82. That means I have a total of 82 actresses who won an Oscar. Then, to get the relative frequency for each age category, my second step is going to be able to take the raw frequency, here 27, and divide it by the sum, which is 82. Sorry for that technical writing error. When we times that by 100, we get 32.9%. This is the percentage of actresses who won an Oscar when they were in the age of 20 to 29. We then repeat this down for each of the age categories to get our completed relative frequencies for actresses. Now, you want to repeat the same process for the Oscar-winning actors. Produce the same thing, then when you've got that, put the two of them together, and when you finish that process, turn on the movie back on again, and let's check our information together just like we would in class. Alright, so you should have a relative frequency distribution that looks something like this. So here we have the age when the Oscar was won, then we have the actresses in relative frequency, and the actors in relative frequency. Notice that the relative frequency should sum to close to 100% for each of these columns. Now, lastly, what conclusions can we draw from this table? Let's take a moment and look at the data. What can we see? When you've jotted down your ideas, turn the video back on and proceed to the next slide. And again, we'll get back together just as we would in class. So, if we look at the age of the greatest frequency of winning an Oscar, we can see the actress's age, where the greatest frequency was 30 to 39, where the actors were 40 to 49. That roughly means that they were looking at somewhere at the age range of a total of 10 years difference. Also, looking at the frequency of winning an Oscar after age 50, actresses were only 9.7% likely to win an Oscar after age 50, where actors were 24.4% likely to do so. This is almost twice the likelihood then, if I'm an actor, of winning an Oscar after the age of 50 than if I'm an actress. This concludes our work with relative frequency distributions. Next up, we'll be looking at how normal distributions connect with relative frequency distributions.